Hello everyone, this is my NMR extra credit video, and I'm just going to analyze a few NMRs for you and kind of explain that whole process. So today I'll be going through ethanol as well as ibuprofen in these two scans, and we'll go over it through number of signals, position of signals, integration of signals, and spin-spin coupling. So the first thing I like to start with is kind of like the structure of ethanol. I know that's what we're trying to find, but because it's ethanol, we already know that. And so the second thing that I like to start with is the number of signals. And so here I'm seeing 3 signals, and I can kind of point them out to you. One of them is right here, the other one is right here, and the other one is right here. And I'll kind of go through those in a second. So I like to label my signals so I can put them in a table as shown below. And so I have the letter that I'm labeling the signal. So for this one, I'm going to put A, I'm going to put B, and I'm going to put C. As I put A, and I put B, and I put C. And so that's kind of how I'm going to go about this analysis. And so for A, we can see here that it is at 1.2, just above 1, so I'm going to put 1.2 ppm. The integration is shown here. It's given. It's at 3H. And so the integration means how many hydrogens are involved. And so for this one, it's going to be 3 hydrogens, which to us can kind of signal that it's going to be a CH3 group. And then next is M for multiplicity. And multiplicity is how many peaks are in your one signal. And so for this one, this is a triplet. So I'm going to write trip for triplet, and the number of neighbors on the number of hydrogen on the neighbors is given by the multiplicity minus 1, because the multiplicity is the number of hydrogens on the neighbor plus 1. So this is going to be 2 hydrogens on the neighbors. And so to make our guess, we're going to fill out the table, then we're going to kind of go back to the guess to verify that. So for B is right here, and B is at approximately 3.6 ppm. It's just above 3.5 right here, and that's going to have 2 hydrogens in the integration, so that's going to mean 2 hydrogens are involved, and it's a quartet. And what that means, and I'm going to write quart. A quartet means that there are going to be 3 hydrogens on the neighbors, again with that n-1 rule, and we're going to come back to the guess as I said. And then for the C peak, which is over here, it's a little tiny one, that's going to be at 3.7 ppm, and it's going to be 1 hydrogen involved, and it's a singlet, and so the singlet means that there's 0 hydrogen on that neighbor. So not on the specific carbon group, but on the neighbor, because the integration is how many hydrogens are involved in that carbon group. So to make our guess, over here, I like to kind of put my pieces of the puzzle here and then combine them into one. And so in order to do that, I'm going to go down to the table that's given and kind of show you. So the numbers that we have are 1.2 ppm, 3.6 ppm, and 3.7 ppm. And so I just like to write those to kind of refresh my memory. As you can see here, I kind of already wrote some things, but I will rewrite them again for us. And so the 1.2 is going to be right here. And so if we kind of just move up in our line, we can see that that's an alkane. These other ones, like the alkene and the alcohols and the amines, are also possibilities. However, my gut's kind of telling me that I'm going to go with the alkane, but I can always go back and check my work if that's not the case. So I'm going to go with the CCH alkane bond for that first one. I'm going to erase these for now. And then the 3.6 and the 3.7, it's kind of clear that the 3.6 is going to be right here, and we just hit right at the alcohol. So that's going to be a pretty strong indicator, again, that the esters and alcohols and ethers are there as well as the halides. However, we can kind of tell based on the molecular formula, if that's given, or the structure that's given, to show that it is, in fact, the alcohol peak. So we're going to go with alcohol, and we're going to write the COH bond right there. So we're going to carry all this information back up with us. So up here, we're going to write our CC bond and our COH bond and our C bond here, because we're not really sure on this one. We did note that it was part of an alcohol, but we're not still quite sure what's going on. And so with this, as I said earlier, the integration indicates how many hydrogen are involved. And so with that, we can kind of say CH3, so this is going to be a methyl group with 2 hydrogens on the neighbors. So it's attached to something with 2 hydrogens. We can't confirm it's a carbon, but we can kind of infer that it's a carbon, and that's going to have 2 hydrogens, and then that would be the other bond that connects somewhere else. We don't know. So this is going to be, so this is going to be an H here as well, and an H here as well. And so, yeah, moving on to the B signal, we can see that B is a quartet, and the number of hydrogens on the neighbors is in fact 3. So we got 1, 2, 3, and now we can see that there's 2 hydrogen involved. And so here that's going to be 2 hydrogen involved on this carbon. And then we've got another one that we just kind of don't know where it's going. And then lastly, we've got 1 hydrogen, and we've got 1 hydrogen here, and on the neighbors, it's got 0 hydrogen. So these 2 carbons up here, they both have hydrogens involved, so we can tell that it's not connected to that. And so it's got to be connected to this, kind of a dead giveaway that it's an oxygen, because oxygen connects to these lone pairs, which would then not give it the ability to bond with the hydrogen. So we can kind of have our puzzle pieces over here. I'm going to move this out of the way. And so we can kind of see this is our methyl group. It's our CH3. Due to our integration, like I said earlier, and just kind of the different puzzle piecing mechanisms that we have discussed. And then this right here is going to be attached to 2 hydrogens. So I'll put the hydrogens actually in a different color. So right here, that's going to be that, because there's 2 hydrogens involved. And so that means that this carbon can make 2 bonds, as seen here in pink. And then lastly, we're going to do this oxygen, or this last hydrogen here, that's going to make 1 bond, which then we can kind of infer that attaches to that oxygen. And so then that will have 1, I'll pick a different color. We've got 1 bond-making capability, we've got 2 bond-making capabilities, and we've got 3 bond-making capabilities. So we're going to start with that middle one, that CH2, and because it has 2 ways to make bonds right here, so we can put that group in the middle because we know that it can form 2 groups. And then we're going to put the oxygen, it really doesn't matter, on one side, and then the CH3 on the other side. And so according to this, then this structure will look like an ethanol. So that is how you get ethanol. And as you can see here, these hydrogens are equivalent, these hydrogens are equivalent, and this one is only 1 hydrogen, but there is no, there's only 3 signals because those hydrogens are equivalent. All of these hydrogens right here are equivalent, these hydrogens are equivalent, and this hydrogen is equivalent. Lastly, I just wanted to point out, like, this hydrogen is the single signal, which is down here on the spectra, and this is because the downfield goes to more electronegative atoms. So I'm going to write more eneg atoms, and then this one is the CH3 methyl group, which is the farthest away from the oxygen. So that is a little bit about how that works, and that's how you can find the structure. Also, I have my little cheat sheet over here that showed our signal when I did this before. So that is ethanol. Moving on to ibuprofen, we can just kind of erase all of this first. But firstly, I just like to count the number of signals again. So here we're going to have 1 signal, 2 signals, 3 signals, 4 signals. Don't forget the bottom one. Sorry, 3, 4, and then we have 5 and a 6 and a 7 and an 8. Don't forget this one. And so that is kind of what this looks like. This is just the blown up picture. So this is going to be signal 1, this is signal 2, signal 3, signal 4, and signal 5, just so that we can see the multiplicity in there. And so after we do that, we can kind of say that we have 8 signals here, 8 signals, just so we can kind of verify that later. And then I like to label them A, B, C, D, E, F, G, and H. So I'm going to write those in here, A, B, C, D, E, F, G and H. Did I forget G up here? No, okay, perfect. And so the first thing, the dead giveaway to me, structurally, is gonna be this spin-spin coupling pattern right here. This is gonna be a doublet of doublets. If you zoom in here, you can see that there is 2 peaks happening, one here, one here, one here, one here. So this is gonna be a doublet of doublets, which to me then tells me that this is going to be a parabenzene. And so this is what that looks like here. Those are the connectors for that. So that's a parabenzene right there, and that's going to be really important later on. So signals F and G, we can also confirm that's a benzene because of the location. It's at the 2 to 7.3 mark, and so we'll just write those in right now, so before we forget at that F and G mark. So 7.2, 7.3, integration is not given, however multiplicity is. The multiplicity is going to be a doublet, and a doublet, so the number of hydrogens on the neighbors is going to be 1 and 1, and so that is how that works for now. And so then my guess is going to be that parabenzene that I just drew up there, with those two. And I'm actually going to spin this around. Ooh. Yeah, I'm actually going to just leave it. So anyways, let's go back to letter A here. So letter A here, it's in the beginning, so I'm assuming it's going to be far away from anything that is electronegative. And so we've got this doublet group here at around 0.9. So I'm going to put 0.9 ppm. No integration, that's not given. The multiplicity is going to be doublet, and so the number of hydrogens on the neighbor is going to be 1. And so I'm not really sure on the guess yet, and we'll come back to that. And so for B, it's also a doublet, so kind of the same. It's going to be at 1.7. No integration again, that's not given. And it's going to be a doublet with 1 hydrogen on the neighbor, and I'm going to leave out that guess. So number 3 down here is really important, so we're going to have to go over here to count those peaks. So 1, 2, 3, 4, 5, 6, 7. So that's going to be a heptet, and that's at just before 2. So I'm going to say 2.8 ppm, no integration, and I said a heptet, so that's going to be it's a multiplet, but I'm going to say heptet, so that's going to be 6H involved. And then next is going to be a doublet, a number 4, so it's going to be 2.4 right there, so that's going to be 2.4. Oh, did I mess that up? Yeah, oh, I'm sorry, this is a 1.8. I'm sorry, apologies. So 2.4 on that doublet right there, and the multiplicity is, yeah, it's a doublet, so it's going to have 1 hydrogen on the neighbor. Let's move on to 5, and if we zoom in over here, 5 is going to be 1, 2, 3, 4, so it's going to be a quartet. Sorry, that's kind of blurry, but yeah, so number 5 is going to be E, so 5 is just before 4 at 3.8, and that's going to be a quartet. So that's going to have 3 hydrogens on the neighbor. So these are all H's up in here. Yeah, all right. And so kind of just taking that pair. Oh, and last but not least, this eighth signal over here at 11 ppm. So this is going to be 11 ppm, and it is a singlet. So that's going to mean it has no hydrogens on the neighbor. This is actually a dead giveaway. We can start making our guesses now. At 11 ppm, as you can see down here, that is a carboxylic acid. So we already kind of know that group, so we're going to have a C, an OH, and a double bond with an O. And so kind of just seeing that, we can identify that group. In addition to that, we can see that the benzene, yeah, you can see that okay, so with that, we can kind of start making our guesses. This 0.9 is kind of telling me that it's an alkene. We can go down here to verify. We'll get all this other stuff out of here. I'm going to keep my red for the carboxylic acid because that's really important. But so seeing that we have a carboxylic acid, we're going to look for an alcohol. But starting with our 0.9 down here, we're going to shoot that up and we're going to see that that's going to be an alkane. So we're going to know that this is going to be an alkane of a sort, but we're not really sure what that kind of looks like yet. We do know that the hydrogen has one neighbor. And so in addition to that, the second one is right next to it. So we're going to also assume that that's going to be an alkane. And seeing that the next signal C right here is a multiplet and it has 6 hydrogens involved. 6 hydrogens divided by 2 is going to be 2 methyl groups. So we're going to have CH3 and a CH3. And also seeing that our two guesses here only have 1 hydrogen on the neighbor. That means that we're going to have a highly substituted group. And so we're going to make this into a CH3 and a CH3 isopropyl group. And so what this means is on this carbon right here, this is only going to have, I'll make that a darker color. Only right here, it's only going to have 1 hydrogen, which would satisfy both of these. So kind of when you see that 6 hydrogen group, you're just going to assume that it's going to be an isopropyl. So this is kind of a given right here. And so we can move on with our little puzzle pieces. And so for D, we're going to move on to D. We're going to look at 2.4. And so the 2.4 is going to lead us right to where we were looking with that alcohol peak. So that alcohol group is definitely present here. So we can go back and look at a little bit more. So this only has 1 hydrogen involved, which would also make sense. And so we're just going to assume that this is a sort of alcohol for now. And so then the next group is going to be that quartet, and the quartet is at 3.8. And so 3.8 right here, we're going to move up, and we're gonna see the alcohol, we're gonna see the ester, we're gonna see a little bit of the carbonyl compounds in this kind of like 3.8 region, and we're gonna see the halides. And so basically we're gonna cross out the halides because we know that we don't have any of those because we're given the molecular formula. So if there's no halides in there, we can cross those off. So we're mainly going to look at the alcohols and esters and the alcohol compounds just because we know that those are in fact present. And so again, you can see kind of the proximity between there. We can just kind of assume that this is also part of kind of the alcohols, but we're not really sure what's going on here. So with our 3 hydrogens on the neighbor, we're going to assume that it's in between something that has more hydrogens, but we're not sure on that yet either. So those are kind of where we're at in that point. If we were going to attach it to this isopropyl group up there, we would have the 6 hydrogens here, and then we'd have a carbon, and then we'd have something else. So we're not quite sure what is going on there. And then obviously we have our, I'm going to make that a different color. Obviously we have our parabenzene group we already identified, as well as our carboxylic acid group that we already identified down here. So these are our puzzle pieces right now, and we're just kind of thinking about our alcohols still, forming our puzzle pieces, but we're going to try and make this structure. So I'm going to make my final structure in purple down here. I'm going to start with my parabenzene because, as you can see, it's got those 2 groups. So I'm going to draw this parabenzene here with those 2 groups, and then I know that my parabenzene attaches to my carboxylic acid because of their proximity on the spectrum, and so that is because the aromatics are right here, the carboxylic acid is right here, and we don't have any other kind of mess in that. So we've got this carboxylic acid, which is right here, which is going to be represented just like this. So we've got our O and we've got our OH. And that's kind of all we know right now, aside from our isopropyl group. And seeing that our isopropyl group is pretty far down in our ppm, down meaning up. Upfield is down here. I'm sorry, that was confusing. And downfield is down here. And so if it's more downfield, it's going to be closer to the oxygens, because those are negative, and if it's upfield, it's going to be far away. So I'm going to put the isopropyl group on the opposite side of the parabenzene here, yeah. So, but the issue here is if you're given the molecular formula, you're going to see that you're missing, so you only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. And so we know based off the molecular formula that you'll be given that there will be more than that. And so that's kind of my process of elimination that I conducted. But aside from that, we also have these 2 to 3 carbons actually that need homes in the structure, which would make sense. So we've got, or 3 locations for these signals. So we've got, this is the carbon with the 6 hydrogen neighbors. So that's carbon, that is the carbon C right there. So this is carbon C. And this is carbon A, and this is carbon B. So those are all taken care of. And then we've got carbon D that has 1 hydrogen. And so to have 1 hydrogen, you're going to have to be highly substituted. And so in order to do that, we're going to have to look at the location again. At D, it's going to be next to the alcohol, most likely. So we're going to take a look at that right here. So we're going to have our 2.4, our 2.4 and our doublet and our 1 hydrogen. And so if this were oxygen, if this were an alcohol compound, it would be not that, because there would have 0 neighbors on there unless this is attached to a CH3 group, which it's not. So, which it is. So this right here, we're going to notice that that attaches to the alcohol, so we can add on another carbon over here with the CH3 group, with that methyl group. So we're going to have a HHH, which is the more downfield. I said 2.4, I meant 3.8. So this is going to be carbon E. I'm so sorry. This is carbon E. This is carbon E right here. That's the same color, green, E. So this is carbon E because it has 1, 2, 3 hydrogens involved. And then we're going to go down because we still have to add another carbon. And so with our parabenzene, we're going to draw that ring again. And that's not how I drew before, so I'm going to draw it differently. And so we're seeing here that we have our 3.8 is pretty significant and our 2.4 is pretty significant. And so the 2.4, we're just going to try and kind of add one down here and see what it looks like, because we have our carbon A, we have our carbon B, we have our carbon C, and then we're just kind of like going to explore with this because there's going to be 2 hydrogens coming off of that. And so in our 2.4 here, there is only 2 hydrogens there, so that's going to be incorrect. And so what we're going to do there is we're just going to leave the isopropyl group where it is, as shown before, with carbon A, carbon B, and carbon C. And we're going to go back up here, and we're going to try some more substitution with some groups. We can see that there's a double bond here, which could contribute to our only 1 hydrogen that we're seeing. And so we could try this with another group there. And so then this one would attach to, and so this carbon right here would attach to this carbon right here, which attaches to the carboxylic acid. And then this carbon would attach to the methyl group out here. So then this would be the CH3, and then this would have the H, and so then that would be satisfied with the 1 hydrogen involved up here. So then this would be carbon D. And so I can kind of just letter these again as A, B, C, and then we have carbon D right here, and then, or I'm sorry, hydrogen regions. I'm calling them carbons. They should be hydrogen regions. Hydrogen region A, hydrogen region B, hydrogen region C, D, and then this one is going to be hydrogen region E as seen here. The carboxylic acid is H, and then the benzene regions are going to be F, which is going to be right here, and then G, because F is going to be down here because it's at 7.2, whereas the G is slightly more downfield at 7.3, and so that's why that is like that. And so to conclude, I just want to re-emphasize that this spin-spin coupling pattern is the parabenzene because of the equivalent hydrogen regions. If the substituent groups were different, it would have 4 signals instead of the 2 that you see there. So that would be one reason why that would not work out there. So that is my extra credit video around NMR analysis. I hope you enjoyed, and I hope that cleared up any confusion.